Hello students, welcome to Fundamental Physics Labs. Today we're going to go over the Optics 04, the interference of light. So this is not so common things that you would see, but however, if you ever blow a soap bubble, you would see fringes that appears here and there. So this is a reflection of a building in front of a very, very thin bubble film. And there's also this demonstration of when you dip a ring into soap water, then as you pull it out, you're going to form a very thin film of soap. So from there, you can actually see these fringes. The fringes that you observe here can be explained by the interference of light. So the interference of light, you could trace it back to the Young's experiment where if you have a double slit, you shine a light in, then as the light goes through this small double slit, then these opening, slit 1 and slit 2, would form its own source, like a circular light that goes through here. So as light comes from here to here, and the other light source comes from here to here, then you can see that there's a path difference of d sine theta here, which is how much different the wavelength travel. So if this distance is exactly 1 lambda, which means the phase of the interference is preserved, so you would actually have the constructive interference between these two sources. However, if it's exactly half a lambda, then you would actually have like the destructive interference because the wave crest meets the other side of the wave, so they cancel one another. But this is when the crest meets the crest, so it constructively interfere with one another. So from there, using a small angle approximation, you could write this equation where you correlate the lambda with the y, which is like the measurement of the pattern that you see on the screen with hash the lengths of the capitalized D. From there, you could actually plot the interference fringes and find the wavelength that comes in, or use the information to find the opening of the slit with the small t. However, we're not going to go over the double slit experiment here today, but today we're going to mostly be working on the thin film. So as light shines through the thin film, so you may wonder, this is not a double slit, so what are the sources that could happen? One source is just like the reflection of the light that comes in and just got reflected back, and another one is when the light goes in and it refracted into the another medium. So when n is the index of refraction, this refraction would actually cause a path difference similar to the double slit. So this path difference, if it's exactly 1 lambda, then you create the bright interference pattern. And if it's exactly half a lambda, then you could actually find that it's actually like the dark pattern that you see here. So you're going to need a microscope to do this. So this is not a common day experiment, but generally if you make the film thin enough, you could actually observe it. However, you can use this information to make the plot from the m, which is the index where you find, let's call this m equals 0. Then you move on to this m equal 1, m equals 2, 3, 4, 5. Then from there, you can actually, as you increase the m, then you can actually track down where is the interference pattern that happens here. So this is one thing that you can do. Another thing that you could do is when you have like a glass plate that are tilted in form of a wedge, then if you find the distance x that is apart from the top here, so this distance x would actually be reflected on what you can see here. So if the light comes in here, it gets reflected. That is ray 1. Another one is ray 2. So this is the path difference here. So by calculating the path difference here, then if n is the air, then n would be 1. So then this path difference here would be what causes the wave number 2 to be on different phase from wave number 1. So if you calculate the phase differences here, then you could actually use the information to find this small wedge angle, theta, or use it to calculate lambda similarly. So if you count the m, which is the order at which the constructive interference happens. So if you have a fine motion equipment, you could actually detect like exactly where are these based on the crosshair that you see here. So this is one way to do it. Another way to do it is if you have like a convex lens here, then the light that comes in, it would get reflected, and the other one would get refracted out. So by having this is what you call the Newton's ring. So then the further away from the center, you would actually have like a bigger path difference between light number 2 and light number 1. So this would create something that looks like what you can see from the anime, you know, but not exactly. So if you put a lens under a microscope with some reflection background, then you could actually create the interference pattern that looks in circular pattern. And again, by calculating the path difference, you could theoretically write down an equation that describes the radius, where you see the fringes, and then where m is the number of fringes that appears away from the center. From there, you can use the information to find the radius of the curvature, or conversely find the lambda. So our setup, you're going to have a sodium light source that is being shined in. So the light source would come in here, and it would hit the beam splitter, which is a piece of a glass plate. And then part of it would be reflected upon the movable microscope. Another one would go into whatever you want to create, the thin film reflection pattern. And then from there, you could actually observe what is the interference pattern from the microscope. So the actual setup would look like this. The light comes in, then you create the patterns here, and then you can observe the pattern. Using the fine motor here, you can actually measure exactly where the light landed on. So part 1, you're going to be investigate the Newton's rings interference pattern to find the wavelength of the right source. So here you need to use the vernier scale to measure the distance using the crosshair. So as you move the crosshair using the vernier scale, then you can actually move it to, let's say, m equals 7. So if you move to the right to m equals 7, then you count the number of fringes here. So if you count the number of dark fringes that appear here, this would be the 7th one. So if you mark this location, you read the reading on the vernier that appears on on the scale. So from there, you would get a very fine reading of the position of the fringes. So so measure the fringes to the right and to the left, then make an average of it. Then based on theory, you wanna square this. So plot m squared versus m, where m is the order at which you observe the fringes. And there, from the slope of this graph, you can actually calculate the wavelength of the source, where n equals 1, because you're actually looking at the air being the intermittent. Okay, so lambda would be slope divided by r. All right. So in this part, you're given r, so you use that r to calculate the lambda. Conversely, on the second part, you are given the lambda, and you can use the exact same relation, doing the exact same plot, and then you could get lambda. You can get r from the lambda that is known. So do this, and you would be able to figure out what is the radius of the curvature at the bottom lens. So here, theoretically, you would replace the one that you already know with the another lens to figure out what r it is for this lens. All right, last part, you need to find the apex angle of the wedge beam. So you can use the relation that you already know. So by, again, using the same apparatus, you could observe this, and you would be able to carefully move these fringes from one to another. So by detecting the location x of the fringes that appears, you can make a plot of x versus m, and from there, use the slope to find the lambda from this relation. Use the slope and the lambda that you know through this relation, you can find what is the opening of this wedge and what is the angle theta. Okay, so that is pretty much it. Thank you, and please enjoy the lab.